All right, guys. Today we're talking about 5.8. Now, 5.8, we talk about scientific notation. And pretty much in a nutshell, what this definition is saying is you have really, really large things out there in the universe. Okay. Like, distances, especially between maybe stars or galaxies. So the universe is a really, really massive place. Okay. Now that's thinking about things on the larger end. Also, you can work backwards and think about things on a really, really tiny end. So many of us have maybe seen the movie like Ant-Man. You guys know where things get insanely small, right? They just keep getting smaller and smaller in like one of those scenes. And so as a result, for our brains to kind of like wrap our head around these massive numbers with a bunch of zeros, or something that's super small with a crazy amount of zeros, what we have is instead what's called scientific notation. Okay. And this essentially is where you're taking really, really massive numbers or really, really small numbers and making it where you kind of have this kind of standard scale where you can at least wrap your head better around these values because they're just so beyond our comprehension. Now, again, with scientific notation, this is pretty key. It's always going to be in between greater than or equal to 1, but then less than 10. Okay, so I would star that or box that. That's pretty huge because that's how we write scientific notation. It's got to be greater than or equal to 1, but it has to be less than 10. And we're going to talk about why that's the case today. Some examples of what scientific notation looks like. So the factor, notice this number right here is greater than or equal to 1, but less than 10, right? If you had to actually kind of put those numbers, put that number in between 1 and 10, you would see 8.3 is in between 1, but it's less than 10 for sure, right? Now, this times 10, we're going to talk about a little bit more why in a moment, has an exponent. Now, sometimes that exponent is positive and sometimes it's negative. Okay. For positive, this is where numbers get really, really big. And when it's negative, you can think of it as that's where it like shrinks down and gets really, really small. All right. Now, here are some examples of some scientific notation. 3.4, notice how that's between 1 and 10 times 10 to the 6th power. 2.1, well, that's in between 1 and 10 times 10 to the negative 11th. And then 5.43, so you don't just have to stop at the tenths place, you can keep going into like the hundredths or thousandths even and beyond, times 10 to the 2nd power. So notice all of these numbers are between 1 and 10, right? And then after that, it's being multiplied by 10 every single time. And then after that, with that 10 has some exponent, whether it be a positive one or a negative one. Again, if you have a positive, this is going to indicate big stuff. But if you have a negative exponent, this is going to become a small item. Okay. Now, this isn't just useful for math. This actually is used in some of your science classes that you'll experience in high school too. Okay. So there's some crossover that happens here that they'll go over into more depth too. But scientific notation, just note you have some number in between 1 and 10 times 10 raised to some exponent. Okay. That is the basic foundation for scientific notation. Now, some examples of what it would not look like. Imagine if you had 42.1 times 10 raised to the 3rd power, let's just say. Well, the reason why that is not an example is because our value here is not in between 1 and 10, right? 42 is outside of that. Okay. And so as a result, what we would have to do, and we're going to practice this today, is make it in between 1 and 10. Another example of what it would look like is if we had perhaps something like 0.34 times 10 raised to the fourth power. That is not an example of scientific notation. Why? Because our value here is not between 1 and 10. It has to be between 1 and 10. In a nutshell, guys, imagine you have some integer and then a decimal place, okay? Or maybe that integer is 3. You have to have some integer and then a decimal place, okay? Another quick example would be something like if we had 40,000. If you just had the number 40,000, I mean, that doesn't even have times 10, right? But the number 40,000, we call that actually standard form, and we'll dive a little bit more later on into that, but that is definitely not in scientific notation, okay? Like if you just gave the number 40,000, well, that's really all it is the number 40,000. There's nothing to do with scientific notation at all there. And so today we're going to practice how to convert things, though, into scientific notation, okay? And the reason for that, why we care about scientific notation, again, it's used to better wrap our heads around these crazy large or crazy small numbers. And then from that, you can begin to compare different values, okay? So for example, NASA guys, they say, okay, what's the distance between this star and this star? They would convert to scientific notation. And then they might calculate the distance between a different star and a different star. Again, they would put it in scientific notation. And then they might be able to say, okay, well, which one's like a further distance? Now, the reason why that's impactful is because then you can do other things with that. Like you can find possibly, other planets that maybe can be housing for life, let's say. Okay. So a lot of times you're using these scientific notations to compare different things after you've converted. All right. Next up, this is really key, and this is really how we do scientific notation. Now, the absolute value of the exponent indicates how many places you're going to move the decimal place. So today we're going to be practicing moving the decimal place if you have a negative exponent. Then you're going to be moving that thing to the left. This is going to make things smaller. Okay. Anytime you have a negative exponent again, imagine Ant-Man just getting really, really small. Okay, quantum realm style. Next up, if it is positive, then that is moving the decimal to the right. Okay, it's getting really, really big. Now, the number itself, when it's in scientific notation and when it's in standard form, those are exactly the same, okay? You're just changing it from scientific notation to standard form. And by standard form, again, standard form is just a number. Like if you were just given a number, all right? It's still the same number. It's just represented differently. That's all. All right, so let's see these in action. And by the way, the reason why you're always going to use scientific notation with this base 10, like why you're always going to see some number times 10 raised to some exponent. The reason why it's always times 10 like that is because we use what's called the base 10 system, okay? You guys have pretty much grown up with that your entire life. You've done all of your math with base 10 systems, okay? So scientific notation wise, that's why we see that. Now, when you have something like 3.22 times 10 raised to the negative 4, all that we're doing, and we're trying to create this in standard form. In other words, we just want the number. Like if you just had to give me, what is that number? What does that come out to be? Right now, it's in scientific notation. We're trying to just get the normal number. Well, because we have that negative decimal place, according to our chart, we are going to be moving that decimal place, negative exponent, we're going to be moving it to the left. So we know we're going to be taking this number right here, 3.22 times 10 raised to the negative 4. And we're going to move this thing left 4 places. That's what that number tells you. So imagine taking your decimal place, which is located right here, and we're going to move that thing 1, 2, 3, 4. And then we put our decimal place. And now anywhere you see those like little bumps, we're going to dump in a little 0. And then just for good measure, a 0 out in front of the decimal place. So this scientific notation form that was straight up given from the beginning boils down to be 0.000322. That is the standard form number. Okay. Next up for B, we have 7.9 times 10 raised to the 5th. So 7.9 times 10 raised to the 5th. All right. Well, that's the same thing as taking your decimal place. Notice how it's at positive this time, right? That's a positive 5 right there. Well, according to our definition, if you have a positive, then we're going to be moving it to the right. You're just moving your decimal to the right direction. So as a result, you're going this way, total of 5 places. So we're going to take our decimal and go 1, 2, 3, 4, 5. Put your decimal. And then anywhere you see those little bumps, just like normal, you throw in those zeros. So it looks like this number comes out to be 790000. Again, commas usually help at this point, help distinguish what it is. So 790,000. All right. And that would be our solution there. Now, between A and B, that's really mostly it, guys. You're just moving decimal places for today. Go ahead, pause the video. Feel free to ask if you guys have any questions at all. All right, let's see some more of these in actions. If you have the temperature of the sun's core, apparently it is 1.55 times 10 raised to the 6th power. And the goal here is to try and convert that into standard form. In other words, what's just the normal number here? Well, if I have 1.55, and usually for these, I kind of like to move my times 10 to the whatever power a little over, so it gives me some space if I need it. So it looks like we have times 10 to the 6. So that's a positive, which means I'm going to the right. Okay. So I'm going to take my decimal place, move it 1, 2, 3, 4, 5, 6 places, because that's my number up here. And then we just dump in our zeros. Boom, 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 boom. So it looks like our value comes out to be 1550000. And then we throw in those commas where they belong. So 1 right there and 1 right there. And that would be our solution. Okay. Now, if you're ever confuzzled and you're like, well, I'm not really sure which way to move the decimal when you're trying to convert to standard, imagine a number line, right? Here's 0. Well, on a number line, aren't all the positive things over here and all the negative things over there? So that you can use that little trick to know, hey, which way do I have to move that decimal? Okay. All right. The lowest temperature recorded in a lab. This is actually pretty interesting. In other words, they're saying basically how cool can something get? Like how much can you freeze an item? So notice how it just says 2 times 10 to the negative 11th like that. Well, the question becomes, where is our decimal place? Where would that actually be at? Fantastic job to those individuals. Yeah, for our decimal place, it is after the 2. And then you can put a little 0 afterwards if you want. The reason for that is if we gave you like the number, well, we'll do like 7. 7 is the exact same thing as saying 7.0, right? So very much the same situation here. Anytime you're given just a number right there, just know that it's whatever that number is and then 0.0. All right. So we have 2.0 times 10 to the negative 11th power. Now, because it says to the negative 11th, we know that we're going to be moving that thing in the left direction 11 spaces. So we're going to take our decimal and go 11 in this direction. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We put our little decimal place there. And then anywhere we see those little bumps, we have zeros. So there, 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 there. All of these places. And so finally, it looks like 0.00000. Hang on. 0.0000002. That would be your actual standard number, and this would be Kelvin. So really tiny number, okay? This is a great example though, where you can see it's like, wow, just trying to comprehend what that decimal is, like in real context, is very challenging for our brains to wrap our head around. Like we don't really quite understand what that means almost. And so that's why scientific notation is super helpful. All right, next up. 4.5 times 10 to the negative 3. Well, we have a negative exponent, so we're moving that way 3 times. So 4.5 times 10 to the negative 3. Again, moving our decimal 1, 2, 3 times. Anywhere that there's a little bump, we've got a 0. And then 1 in front for good measure. So 0.0045. Okay. That would be our solution there. Now, what happens when you have something times 10 to the first? So we have 3.69 times 10 raised to the first power. Well, that number 1 is still a positive 1, right? So you're still going to move to the right 1 unit, so 1 decimal place. So nothing really changes there, okay? You're still moving your decimal place over 1. And what we're left with is 36.9. And that would be your final answer there. Okay. A little bit of a special guy, but not crazily different. All right, what I would love for you guys to do is to go ahead, please try G through J. Go ahead, pause the video, try them out, and then we'll come back together and see how we did. All right, fantastic job to those students. So we have 4.59 times 10 raised to the 7th power. We're going to move our decimal over to the right 7 places because we have a positive 7. So 1, 2, 3, 4, 5, 6, 7. Put our decimal at the end. Anywhere we see those bumps, fill them in with zeros. Final answer comes out to be and then our commas. So it looks like 45,900,000. For H, and we have 2.14 times 10 raised to the negative 3rd. Because we have that negative exponent, we are going to the left 3 places. So 1, 2, 3, put our decimal place, fill in with zeros. And so our final answer comes out to be 0.00214. For I, we have times 10 to the negative 5, so we know we're moving to the left 5 units. So we have 5.01 times 10 to the negative 5. We're going to take our decimal place, move it to the left 5. So that's 1, 2, 3, 4, 5. And then anywhere we see those bumps, throw in the zeros. And then a 0 out, 1 in front of the decimal, like that. We have 0.00000501. Yes, you do need that 0.1 at the end. Okay. And so that would be our final solution there. And now for J. 8 is really the same as 8.0 times 10 to the 8th. Because that is a positive 8, we are moving to the right 8 decimal places. So 1, 2, 3, 4, 5, 6, 7, 8. And then we put those zeros in for the little bumps. And so when we do that, we have 8, 0, 0, 0, 0, 0, 0, 0, 0. Commas where they belong, though. Boom. And boom. For a grand total of 800 million as a standard number. Fantastic job to those students. Are there any questions at all on any of those 4? Go ahead, feel free to pause the video and ask. All right, on the you try it is 12 times 10 to the 4th written in scientific notation. Go ahead, please pause the video, try 1 and 2, and then we'll come back together and see what we got. All right, so for number 1, we have it is 12 times 10 to the 4th in between. I'm sorry, is that written in scientific notation? Fantastic job to that individual. Got no, it's not, because our number here is not between 1 and 10. Has to be between 1 and 10. So no, because our value 12 is not between 1 and 10. Okay. Now, writing these in standard form. Remember, standard form is just a normal number. Okay. So if we have 6 times 10 to the 7th power, that is really the same thing as saying 6.0 times 10 to the 7th power. And what we're going to do is we notice that we have a positive 7, so we're going to move it over to the right 7 places. So 1, 2, 3, 4, 5, 6, 7. We're moving our decimal 7 places to the right. And then we just dump in a 0 anywhere where we see those bumps. And so when we are done, we end up with 6, 0, 0, 0, 0, 0, then 0, 0. for a grand total of 60 million. Okay. Now on the practice, I would ask that you guys do those two different steps. One for the bumps like that, and then one is like kind of a nice clean number with all the commas and everything. Okay. So that's what I'm looking for. Next up, 9.9 times 10 raised to the negative 5. So we have 9.9 times 10 to the negative 5th. Well, looks like because we have a negative exponent there, we're going to shift this to the left 5 units. So we would take our decimal place and move it 1, 2, 3, 4, 5 decimal places. Anywhere where we see those little bumps, we throw in a 0. And then that 0 extra one in front. So final answer is 0.0000099. Okay. And then for number 4, 1.28 5 times 10 to the 4th power. We do see that we have a positive 4 here, so we are going to the right 4 places. Taking our decimal, moving it over 4. 1, 2, 3, 4. And then throw a little 0 there. Anywhere where those extra bumps. So our final answer is 12850 with a comma right there. Okay, again, 2 lines for each question like that, okay? Just make sure you're doing both. One for the bumps, one for the final answer with commas. Are there any questions at all on 1 or 2? Feel free to pause the video if you need to and ask. All right, here we are at example 2. And on this one, we're going to be looking at densities of objects. So it says an object with a lesser density than water will float. An object with a greater density in the water will sink. And so we're asked to use each given density in kilograms per cubic meter to explain what happens when you place a brick and an apple in water. Many of us recall when we were younger, bobbing for apples, right? Notice how they floated to the top usually. But if you put a brick in water, we know that it would sink down. Using scientific notation, though, we can actually calculate those densities as a standard number, okay? So for water, when we see 1.0 times 10 to the 3rd, we have 1.0 times 10 to the 3rd, because we have a value that is positive here. We're going to be going over to the right. We're going to move our decimal over to the right. 1, 2, 3. And then anywhere we see those little bumps, we're going to throw in the 0. So the density for water in standard form would be 1,000. Okay. Next, for the brick, we have 1.84 times 10 to the 3rd. Very, very similar scenario. We're going to move that decimal over 3 times. So 1, 2, 3. And then anywhere there's that 0, or anywhere we see that bump, we put a 0. So we're looking at a density of 1,840. And finally, for the apple, we see that it is 6.41 times 10 to the 2nd. Now, because that is a positive 2, we know that we're going to go to the right 2. So we're going to move our decimal over 2, giving us 641. Now, each of them are in standard form. And so what we're going to do next is compare the densities. So notice how the brick value in standard form is larger than the water density, that's where we see it sink. Okay. Whereas the Apple one is smaller, so that's why it floats. All right. Any questions at all on example 2? All right, what I would love for you guys to do next is to go ahead and pause the video and let's go for you trying this one, and we'll stop at those 2 for right now. So go ahead and try those first 2. If you're feeling really ambitious or you're thinking this is light work, you can go ahead and try this one too. So go ahead, pause the video, try them out, and then we'll come back together and see how we did. All right, so for example 2, what we have is the density of lead is 1.14 times 10 to the 4th kilograms per cubic meter. So what we want to do is calculate what is the standard form for that value. So we have 1.14 times 10 raised to the 4th power. Because that 4 is a positive 4, we're going to move to the right, that decimal. So we have 1, 2, 3, 4, and then anywhere that there's those little bumps, we throw in the zeros. And so writing out the standard form value, we end up with 11,400. Now, what does that actually mean? Well, we can use our 2 standard form values, one from the water and one from the lead that's placed inside the water. So this value right here. And then compare the 2. Well, notice how the lead one is actually bigger, right? 11,400 is a much bigger number than 1,000. As a result, what would happen there is you would see it sink to the bottom because it's heavier. Okay, so our lead, to answer the question, our lead, when placed in water, would sink to the bottom. Okay. For our second one, we're asked to estimate the population of the United States is 3 times 10 to the 8th power, and the population of the world is 7 times 10 raised to the 9th power. How many times larger is the population of the world? So in the United States, what we're going to go ahead and do is transition this value into a standard form. Right now it's in scientific. So we have 3.0, this is for US, times 10 raised to the 8th power. Let's go ahead and calculate what is that standard form. Well, because we have times 10 to the 8th, that is a positive 8. So we're going to move the decimal over to the right. We have 1, 2, 3, 4, 5, 6, 7, 8. And then anywhere where we see those little bumps, we throw in zeros. So for the US, we have, should be about 300 million. So looks like 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7. So we need one more, 8. All right. So we are looking then at 300 million. I know that's much larger at this point, but for this question, it is 300 million. Now we have to figure out the world's population. Well, according to this, the world's population is 7 times 10 raised to the 9th power. So 7 times 10 raised to the 9th. It's really the same as 7.0 times 10 to the 9th. And we're going to move that decimal over to the right 9 places because we have a positive 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And then anywhere where we see those bumps, we throw in the zeros. So 1, 2, 5, 6, 7, 8. Maybe we're 9th. So it looks like There's our value. And then our commas. So we are looking at 7 billion people roughly on the earth. Now the question becomes, how much larger, or how many times larger is the world population? Well, how would you find, if you have the US's population compared with the world population, how would you find out how many more times the world's population is by larger? Awesome job to that individual. It was suggested just take the world population, 7 billion. That's 1, 2, 3, 4, 5, 6, 7, 8, 9 zeros. And divide it by the US's population, so 300 million. So. And then what you can do very, very nicely and easily, especially with standard form, is start to cross off zeros. Make your life easy. So looks like it boils down to be 70 over 3. So that's about what, 23 times and a third, roughly. So 23 and 1/3 times bigger. So compared to the world, the US has some population, but there's a lot more out there. Okay. That's kind of crazy to think about. There's really that many more people out there in the world compared to the US, because the US is a pretty big place. So I know like in India, I think that they have like a solid billion people or something like that. And I think China also has like at close to 1 or 2 billion, somewhere around there. So there's a lot of like more dense areas too, populations. All right, next up, we're looking at a year is about 3.156 times 10 to the 7th seconds. All right. So the question becomes, well, how many seconds are in 5 years? Well, what we can go ahead and do is find out what is this standard value. So we have 3.156 times 10 to the 7th power. And because that is a positive 7, we're going to move our decimal to the right 7 spots. So we would go 1, 2, 3, 4, 5, 6, 7. Throw in those zeros in, where we see those bumps. Ending up with 3, 1, 5, 6, 0, 0, 0, 0. And then putting those commas in. Now, that is for 1 year. That's how many seconds you have. Well, if you wanted to find it for 5, all you'd have to do is do what? Very good to that individual. We're going to take that value, multiply it by 5, and see what we get. So go ahead, pause the video, type that in the calculator, or multiply it out. What do we end up with? Awesome job to that individual. So you should have gotten this value right here. Okay. Now for B, it says how many seconds are in a half of a year? A half of a year. So how would you actually calculate that now? Awesome job to those individuals. They suggested pretty much taking how much it is in 1 year and the first suggestion was multiply by 0.5. And then the other path was taking our value and dividing by 2. These mean the same exact thing. You will get the same result in the end. So what is our 31,560,000 times 0.5? What would we get there? So that is the value that we ended up with, 15,780,000. Now again, for the blue, if you did this path instead, you would see the exact same conclusion. So really specifically, we should say seconds. Okay. So same exact result. Now, likewise in this one, there would be that many seconds. All right. Now, when it comes to time, guys, you're going to realize, if you haven't already, that time starts to fly by, especially as you get older. So yes, that seems like a lot of seconds, and I would encourage you to seize every single moment in life. All right. Trust me when I say it will fly faster than you realize. So take advantage, seize the day, enjoy it, work hard, go forth, do great things.